In this video, we introduce the dot product starting from the geometric view, and then we semi-formally work out the algebraic formula for the dot product in terms of the vector components. And finally, we apply the dot product to computing vector magnitudes and angles between vectors. So we start with a picture of two vectors, v and w, and there's an angle of theta between them. We want to compute this new thing called the dot product. It's written as v dot w. So both of the participants in this sort of product are vectors, but what pops out is vw cosine theta, and that's the magnitude of v. That's just a v with no arrow over the top. Magnitude of w times the cosine of the angle between them, and that is a scalar, which is actually the first point on this list on the right. Now there's a couple different ways of interpreting this geometrically, and the first is to gather the v and the cosine theta together in parentheses and multiply that by w. Well, what's v cosine theta? That's the magnitude of the adjacent component of v. That's the hypotenuse multiplying the cosine of the angle theta. So the dot product gives us the magnitude of the parallel component of v in the direction of w, then multiplied by the magnitude of w. There's another way to look at it though. If I take my dot product and I gather the w with the cosine theta, well, w cosine theta is the component of w in the direction of v. So now I'm interpreting the dot product as the magnitude of v multiplying the magnitude of the parallel component of w in the direction of v. So how about this list on the right? The first point is that the result of a dot product is a scalar. And this is why the dot product is sometimes also called the scalar product. My second point, if the angle between the vectors is 90 degrees, the dot product vanishes because the cosine of 90 degrees is 0. Third, if the angle between the two vectors is 0, the dot product is maximized. The maximum value of cosine happens at 0, and it's equal to 1 there, so the dot product would turn into simply the product of the magnitudes, VW. Fourth, the dot product is commutative. And this is kind of the one-line proof of that. V dot w is VW cosine theta, but scalars are commutative, so I could reverse the w and the v, and now I'm looking at the definition of w dot v, so v dot w is equal to w dot v. Fifth, and this is the one that we're not going to prove, the dot product is distributive. So the proof of that requires the law of cosines, and that's the one piece we're skipping today, which is why I called it a semi-formal derivation. Sixth, the dot product of a vector with itself gives the squared magnitude of that vector. So if I dot a vector into itself, the angle between the two vectors is 0 because they're pointing in the same direction, and I just get the magnitude of the vector times the magnitude of the vector again, and that's the squared magnitude of that vector. And our seventh point before we move on is to take a look at dot products between our standard unit vectors. Remember, a unit vector has a length of 1. I hat points in the positive x direction, j hat the positive y direction, k hat in the positive z direction. If I dot a unit vector into itself, I get 1 because I get the square of the magnitude of the vector. If I dot between two of these standard unit vectors, well, they're at right angles to each other, so those all vanish. And that's going to be useful when we try to get an algebraic formula for how the dot product works. So how do we get a dot product between two vectors if we know their components? We're presented here with two vectors written as row vectors, and we want to get the dot products in terms of all those components, vx, vy, and vz, wx, wy, and wz. And it's useful here to write these in I hat, j hat, k hat notation. Now we dot the two vectors into each other, and this is where we use the distributivity of the dot product, that one piece that we didn't prove in this video. If I know that the dot product is distributive, then that means I get 9 terms out of this. I'm going to get a vx I hat dotted into wx I hat. I'm going to get a vx I hat dotted into wy j hat. And that first term would give me a vx wx times I hat dotted into itself. The second term, a vx wy and an I hat dotted into a j hat. And the third term would have an I hat dotted into a k hat. Now, of course, we just established that if you start dotting between these standard unit vectors, all those dot products vanish. And then if you dot a unit vector with itself, you get 1. So I'm not going to write every single one of these terms because now I realize that if I'm dotting between unit vectors, those all vanish. So when I start distributing this second term, the only survivor is going to be the vy wy, j hat dotted into itself, which gives me a 1, the others vanish. And then finally, when I distribute the vz k hat, the only survivor there is vz k hat dotted into itself. And the other terms that have a mixture of two different unit vectors, those vanish. So in the end, I get vxwx plus vywy plus vzwz. And that's how we're going to compute a dot product given the coordinates of two vectors. To wrap things up, we'll work an example where our vectors are given as column vectors so we know their coordinates. And we're asked to get the vector magnitudes. We're asked to compute the dot product between the vectors. That's the formula we just got. And then finally, we're asked to compute the angle between the two vectors by going back to the geometric interpretation of the dot product. So one way to look at the magnitude issue is that I can get the squared magnitude by dotting each vector into itself. So v squared is going to be the dot product of v with itself. According to our new formula, I multiply the x components of the two vectors I'm dotting, and I'm dotting this into itself, so I get a -1 squared. And then I add to that the product of the y components, which would be 3 squared, and I add to that the product of the z components, which would be 1 squared. And that's a 1 plus 9 plus 1, so that's 11. And when I square root it, I get square root of 11 for the magnitude of v. I do a similar thing for w, dot it into itself. That's 0 squared plus 1 squared plus -1 squared. That gives me a 2, and when I square root, I get w equals root 2. In part B, I want to get the dot product v dotted into w. And again, I just take the products of the components pairwise. So v dot w is going to be -1 times 0 plus 3 times 1 plus a 1 times a -1. And the first term vanishes, and I get a 3 minus 1 or a 2. So the dot product between them is 2. Finally, I want to use the dot product to compute the angle between these two vectors. So what we're using here is the geometric interpretation of the dot product. V dot w is vw times the cosine of the angle between them. And now I know what v dotted into w is, that's 2. And I know the magnitude of v, that's root 11. And I know the magnitude of w, that's root 2. All that's left is that angle. So these can be combined as root 22, and I'll divide by that. And cosine theta is going to be 2 over root 22. And then I invert the cosine function, and I get approximately 64.8 degrees, separating these two vectors in 3 space. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.